In this lesson, we discussed the definite integral. So in a previous lesson, we were discussing approximating the area underneath a curve of a function. And we were using Riemann sums. So in this lesson, we consider the limit of our Riemann sum as the subintervals approach the width of our subintervals are approaching 0, and the number of subintervals goes to infinity. In other words, these rectangles are becoming thinner and thinner and thinner, and the number of rectangles is approaching infinity. Remember, this is the sigma notation we were using to approximate the area. So this is the sum of each of the areas of the triangles. F of C sub k, it represents the height of each rectangle, and C sub k is some point within each subinterval at which we are evaluating our function. This is giving us the height of our rectangles, and delta x represents the width of each rectangle. Now, if we let the number of rectangles go to infinity, and we're allowing delta x, the width of our rectangles, to approach 0, then what we can do is we can consider the limit as n goes to infinity of the sum of f of c sub k delta x as k goes from 1 to infinity. And this is going to be our definition of, or what is meant by, the integral, the definite integral from a to b of f of x dx. Now this symbol here is called the integral, and its origin comes from the letter S, which represents sum. This here is called the integrand. F of x is called the integrand. So it's telling us what we're integrating. And dx just represents the variable of integration. So we're integrating with respect to x. A here is your lower limit of integration, and B is your upper limit of integration. So this is what we have. So this is the meaning of the definite integral. Now the following is a list of rules that the definite integrals follow. The first is the order of integration. So this would be the integral of f of x dx from b to a, and this is equivalent to the opposite of, or the negation of, the integral of f of x dx from a to b. So notice that for this one, you're going from b to a, and if you turn that around from a to b, it's going to be the negation of, or the opposite of, a to b. The negation of the integral from a to b. So basically, we're integrating backward here. That's what this is. And our delta x values would be negative because we are integrating backwards. All right, let's talk about the zero width interval. So here we would have the integral from, or the integral of, f of x dx, watch this, from a to a. And this would just be 0, right? Because you're going from a to a. So this is why it's called the zero width interval. Your delta x is just 0. The constant multiple, so this is the integral of f of k times f of x dx from a to b. This is equivalent to k times the integral from a to b of f of x dx. Cool. There's a few more that I would like to give you now. The next one is kind of like 2 in 1 here. So it's a sum and difference. So we can really just combine these two rules. So it's the integral from a to b of f of x plus or minus g of x. This is your integrand. Let me put all of that in parentheses. Dx. This is equivalent to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. The next rule is the additivity rule, and it basically says that the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Well, all of that is equivalent to the integral. Notice here you're going from a to b and then from b to c. So let's just go from a all the way to c, right? So from the integral from a to c of f of x dx. And the last one I want to discuss is the domination rule. So if we're given that, or if we know that f of x is greater than or equal to g of x on an interval, let's say from this interval from a to b, then, so I'll just say that implies that the integral from a to b of f of x dx must be greater than or equal to the integral from a to b of g of x dx. All right, very good. To illustrate some of the rules, let's consider the following. Suppose that we know that the integral from -1 to 1 of f of x dx is 5, and the integral from 1 to 4 of f of x dx is equal to -2, and that the integral from -1 to 1 of h of x dx is equal to 7. Then, what would the integral from 4 to 1 of f of x dx be? So notice that all we are given here is the upper and the lower limits are swapped, right? Up here you have the integral from 1 to 4. 1 is the lower limit, 4 is the upper limit of f of x dx, and that's equal to -2. If you swap these limits, and instead of going from 1 to 4, you go from 4 to 1, what that's going to do is that's going to negate your area. So then this is equal to the negation of the integral from 1 to 4, f of x dx. So basically, it's going to be the negation of -2. So the answer is +2. Let's consider the following. What about the integral from -1 to 1 of 2 times f of x plus 3 times h of x dx? Well, I think the first thing we would want to do is we would want to use the sum rule here, and we can take the integral of 2 times f of x, and then we'll evaluate the integral of 3 times h of x. So let's see if we can walk through this. This would be, I'm just trying to move the screen here so that we can maximize the space. There we go. All right, so then this is equivalent to the integral from -1 to 1 of 2 times f of x dx plus the integral from -1 to 1 of 3 times h of x dx. And then I can, so that was the sum rule. Now I can use that constant multiple rule to say that this is equivalent to 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. Now, let's not forget that this was given, the integral from -1 to 1 of f of x dx, this is all equal to 5. And the integral from -1 to 1 of h of x dx is equal to 7. So we can substitute. So this is 2 times 5 plus 3 times 7. So then this is 10 plus 21. So then this is 31. That's our answer. Pretty cool, right? Let's look at maybe one more. Let's look at the integral from -1 to 4 of f of x dx. Now, notice that what was given was, this is not given, not -1 to 4. But what is given, I'm going to see if I can scroll all the way back up to the given information. Here it is. When it comes to f of x, we are given from -1 to 1 and then from 1 to 4. So what we can do is, instead of, what they're asking us right now is from -1 all the way to 4. Well, we can break it up and say, well, we know what the integral is from -1 to 1, and then we know what the integral is from 1 to 4, right? So let's go back to our problem down here. Where is it? There it is. So then what we can say is, this is equivalent to, and this is using the additivity rule, this is equivalent to the integral from -1 to 1 f of x dx plus the integral from 1 to 4 f of x dx. So basically we're breaking it apart and adding it piece by piece, right? And so this is given, this is 5, and then this integral here is -2, and so then the area, or the integral, is equal to 3. All right, folks, this definition is really important. If y equals f of x is a non-negative and integrable, if it is non-negative and integrable over a closed interval from a to b, then the area under the curve over that interval from a to b is the integral of f from a to b, right? So this integral here from a to b represents the area underneath the curve, which is exactly what you and I were doing or considering in earlier lessons. So this is the first time we have a rigorous definition for the area of a region, okay, whose boundary is the graph of a continuous function. All right, very good. Now we can use this to calculate the area under curves. All right, check out this example. Let's compute the integral from 0 to b of x dx and find the area, let's call it a, under y equal to x over the interval from 0 to b. All right, and we're assuming that b is positive. Let's draw a picture so that we can see exactly what's happening here and what they're asking. Okay, so they've given us this identity function, really, is y equal to x. That's what it is, the identity function. And this is the area here. I can label it A. There. So this is the area that they're looking for. The area underneath y equal to x from 0 to b, and b is just some positive value along the x-axis. So there's a couple different ways we can do this. I mean, this area here is a triangle, and we have a traditional formula for the area of a triangle. But let's see if we can compute the area using the limit of Riemann sums. So this is what we're going to do. We know that we can say that we're going to evaluate the sum of, let's see, f of, remember we wrote this c sub k delta x, right? Where this is the height of our rectangles and this is the width of our rectangles. And we're going to let k go from 1 to n. These c sub k values are points within each subinterval. And what we're going to do is we're going to allow the width of our subintervals to approach 0, and we're going to let the number of rectangles approach infinity. So let's talk about these subintervals now. In other words, let's discuss how we are partitioning our interval from 0 to b. So we did this earlier. If this is 0 and this is b, then if we choose to use subintervals that have the same width, and let's call that width delta x, then we know that the width here, if I can just get, there we go. We know b minus 0 divided by n will be the width, right? This is the right endpoint of our interval, the left endpoint of our interval, divided by n, the number of partitions. And so then this would be b over n. This here, folks, represents, here I can write it, this represents delta x, the width of our subintervals. So then that means our first subinterval will be from 0 to b over n. Our second interval will be from b over n to 2b over n, right? From 2b over n to 3b over n, and etc. Until we get to the right endpoint, which I can write it as nb over n, which is the same thing as b, right, everybody? So this is how we're partitioning our interval from 0 to b. Now we have to choose a point from each subinterval, and to make it just pretty straightforward, what I'm going to do is I am going to choose, let's see what I can do. Oh, I can choose the right endpoint from each subinterval. I could also choose the left endpoint, folks, but let's go ahead and choose the right endpoint. And so in this first interval here, excuse me, we'll use the right endpoint for c sub k. For the second interval, we'll use 2b over n, the right endpoint. For the third interval, we'll use that right endpoint, 3b over n. So what that means is this is equal to the sum as k goes from 1 to n of, let's see, k b over n times b over n. All right, let's talk about that. Delta x is the width. I showed already that that's b over n, so that's where the b over n comes from. And remember that our function is just y equal to x. So whatever you plug in for x, that's what you get out. It's the identity function. If you plug 5 in, you get 5 out. If you plug 10 in, you get 10 out. So whatever you plug in, that's what you get out. It's the identity function. So if I'm plugging in, b over n, I'm going to get b over n out. If I get 2b over n, if I plug that in, right, I'm plugging in my right endpoints. If I plug this in, then I'll get that out. If I plug in 3b over n into my function, I'll get 3b over n out. And so this k b over n, I'm letting k run from 1 to n, right? And so if I let k be 1, then this is 1b over n, or b over n, the first right endpoint. And then when I let k be 2, right, this is 2b over n, the next right endpoint. When I let k be 3, this is 3b over n, the third right endpoint, right? So these are the heights of all of my rectangles. This is the width of my rectangles. All right, very good. Let me make some board space here. Okay, so this is equal to, let me see if I can, yeah, this will be good. This is equal to the sum as k goes from 1 to n of k b squared over n squared. Now, k is our index of summation. And this expression, the b squared over n squared, is not dependent on k, so I can pull that out as a constant multiple here. So b squared over n squared times the sum of k as k goes from 1 to n. But this is just the sum of the first n integers, right? We can use Gauss's formula here. Remember we mentioned Gauss's formula for the sum of the first n integers. It is n times n plus 1 over 2. That's the sum of the first n integers. Okay, so let's continue simplifying. We're just moments away here. So then this is equal to b squared. We can rewrite this as b squared over 2 times, let's see, this up here, let's see. I can rewrite this as n squared plus n over n squared, and then I can continue simplifying. So then this is equal to b squared over 2 times n squared divided by n squared is 1, and then n divided by n squared is 1 over n. All right. Now this is where we bring in the integral. All right, so this is what we're going to say. By definition, the integral from 0 to b of x dx, by definition, this means the area underneath this curve from 0 to b is equivalent to the limit as n goes to infinity of the sum of f of c sub k delta x, right, as k goes from 1 to n, which is equivalent to the limit as n approaches infinity of b squared over 2 times 1 plus 1 over n. And as n approaches infinity, this ratio, 1 over n, approaches 0. And so this is just b squared over 2 times 1, which is just b squared over 2. That is the area underneath that curve, that triangular area. Now we can confirm this because let's go back to our picture. Where is our picture? There it is. Look at this. We know that here, I think I can squeeze it in right here. The formula for the area of a square, a triangle, is 1/2 times the base times the height. But because this is the function y equal to x, your base here is, can I mess up our picture a little bit? The base here is b, and the height is also b, right? So then 1/2 times the base times the height in this example is 1/2 times b times b. That is to say, b squared over 2. That's the area of this triangle, the area underneath this curve. And that's exactly what we got using an integral. Isn't that pretty cool? Okay, check out this example. We want to graph this integrand. This is the integrand, the square root of 9 minus x squared. And then we're gonna use a known area formula to evaluate the integral. All right, so let's graph this. What is this equal to? Well, consider y equal to the square root of 9 minus x squared. That's equivalent to y squared is equal to 9 minus x squared, which is equivalent to x squared plus y squared is equal to 9. And this is a circle whose center is at the origin, right? And whose radius is 3. So, but it's only the upper half, right? It's y equal to the square root of 9 minus x squared, y equal to the positive square root, the principal square root. So it's only the upper half of that circle. So let's draw that now. All right. Radius is 3 units. Hopefully I can make this circle look half decent here. So it's a semicircle. All right, so this is the area they want us to consider, right? Let me go back up to our integrand. There it is. So this is from -3 to 3. It's the area underneath that semicircle. So let's use a known formula. Well, we know that the area of a circle is pi r squared. So therefore, the area of this shaded region would be half of pi r squared, right, everybody? So then it'll be, because this is only half the circle, so it'll be a half of pi times 3 squared. So then this is going to be equal to 9 halves pi squared units, right? Or 9 pi over 2 squared units. This is an exact answer. All right, that was so fun. I think we should do another one. Okay, folks, here's a brand new integrand. We want to graph it and then use a known area formula to evaluate this integral. All right, so this is a line whose slope is -2 and whose y-intercept is 4, and we're going from 1/2 to 3/2. Okay, so let's actually consider when you plug in x equal to 1/2, what do you get? Here we can actually evaluate that. So -2 times 1/2 plus 4. What is that? That is -1 plus 4, so that's 3. So we'll go to the point 1/2, 3, and then we're going to plug in 3/2. So then this is -3 plus 4, so then this is 1. Okay, so we'll go to the point 3/2, 1. So let's graph this line. All right, so here we go. So 1/2, 1, 3/2. Okay, 1/2, 1, 3/2. 1. Maybe I could make this y-axis longer. 1, 2, and 3. Okay, so excuse the sloppy graph here. So anyway, 1/2, 3, right? And then 3/2, 1. So something like this. So then here's our graph. This is a line, right? Remember let me go back up to our line really quick to remember. Yeah, so the y-intercept is 4, so this line is going to intersect the y-axis at 4. It'll hit the x-axis at +2, right? If we plug in 2, -2 times 2 is 4, -4, -4 plus 4 is 0, yeah. So at x equal to 2, so over here, it'll hit the x-axis. But anyway, the area that they're asking us to consider is from 1/2 to 3/2. So it's this area. Oh, look at that. This is a trapezoid. This is a trapezoid. So we are asked to find the area of a trapezoid. Isn't that fun? All right, so here we go. The area of a trapezoid is 1/2. Oops, sorry. Okay, there it is. 1/2 times the sum of the bases. I don't know how you remember the bases. I'll call one base lowercase b and the other one capital B, okay, times the height. Okay, how you write the area for the trapezoid might be a little bit different, but this is the area of the trapezoid. So therefore, this is 1/2 times. Okay, so let's call this one base, and the other base is over here. The bases are these the only one, the one pair of parallel sides, right? That's what makes this a trapezoid, is that you only have one pair of parallel sides. So this distance here, we already figured it out, that when you plug in 3/2, you get 1. So this distance here is 1. Plus the larger base is when you plug in 1/2, and we did that, and you get 3. So then this is 3. And the height, now the height is going to be this distance here. This is your height, and it is 3/2 minus 1/2. So that's 2/2, which is 1. The height is 1. So then this is 1. So then the area is half of 4. So then the area of this trapezoid is 2 square units. 2 square units. 2 square units is the value of our integral. Where is it at? There it is. This is equal to 2 square units. Okay, this integral from 1/2 to 3/2 of negative 2x plus 4 dx is equal to 2 square units. It's the area underneath this line, which forms a trapezoid. And that was fun.